All right, we're going to look at 3, 4, 3 together. Kind of take a step back calculus day. This is a good video day. We're going to kind of look at these individually, make some graphs, get some talking done, do some work. So we're going to start with number 170, Funky Functions Part 2. One of the reasons we need to analyze functions analytically is because graphs can be misleading. So let's look at these graphs. We looked at one yesterday that looked like that was that graph they're mentioning with the 2 plus the absolute value of x squared. If you just looked at it, it kind of looked like that. But when we zoomed in there, we ended up getting this little cusp going on there. And we talk about those cusps being non-differentiable. So let's look at these graphs. Sine x over x. We've actually graphed this quite a few times. That looks like, this. We put it in our calculator. It looks continuous, but of course we know at 0 it's non-continuous. But anytime a function looks continuous, it's going to have a hole here. And yesterday we looked at graphs, and if a graph has a hole, that is a non-differentiable point. So our answer for A would be it's non-differentiable because there's a hole. So there's several different ways of having non-differentiable. One is a hole. Let's look at this graph in B. This is kind of a cool one to put in your calculator. Let's take a look. When we put in our calculator, we get kind of a little loopy here. Comes up, comes down, comes up. And we're specifically talking again at 0. And when we zoom in at that 0, we get that same sketch we've been looking at where it gets really steep there. And I'm going to zoom in there, and it's going to come through 0. And what does that mean when we have that steepness going on there? That would mean it is a non-differentiable. And the reason is it's a vertical tangent. Vertical lines have no slope and are non-differentiable. And then let's look at this third one. I like talking about this graph because it kind of brings in our transformations idea as well. If you just had a parenthesis, x cubed plus that 0.125 in it, it's either going to go left 0.125 or maybe even up 0.125. In this case, it's really both. So specifically, we're talking about at the negative 0.5. And we talked about how to start graphing these absolute value things where we can really just call this, a piecewise where it's going to be the negative x cubed plus 0.125 when it's, in this case, x is less than negative 0.5, and then it's going to equal x cubed plus 0.125. So we just do the plus and the minus of the x. X is in the absolute value when x is greater than negative 0.5. And now we would get this 0.5 when we actually kind of set this equal to 0. If I set x cubed plus 0.125 equal to 0 and I subtract it over, I get the negative 0.125. And if I take the cube root, that's where I get the negative 0.5 from. So that tells me like where my graph breaks at, I guess. So again, if we zoom in there, and if we just zoom like standard, we get that, we get kind of a parabola looking thing. But if you zoom in at that negative 0.5, you do see what goes on there. And it does happen to be that little cusp going on there. And really, like if I kind of change colors here, if we were to graph our normal x cubed plus 0.125, that looks like this. So I guess if I just graph that absolute value, kind of like we've been doing on the worksheets, this part of it's just going to end up going up here. So you should be able to see that cusp right there. So again, I'm saying it's non-differentiable. And this one has a cusp. So we had a hole, we had a vertical asymptote or a vertical tangent, and we have a cusp. All non-differentiable.